You know, it's pretty wild how sometimes one single idea can literally change the world. Back in 1970, a researcher at IBM, E.F. Codd, published a paper. It wasn't some huge book, just a dense, kind of academic paper. But that one paper, it's the reason almost every database, the things that power our entire digital world, works the way it does today. So let's get into it and really understand the paper that organized the digital age.
I mean, just listen to that. This one sentence is pretty much the entire mission statement of Codd's paper. Before he came along, getting information was like being a librarian who had to know the exact physical shelf, the exact box, and the exact order of the files just to find one little thing. It was insane. Codd's whole mission was to completely shatter that system. His goal was freedom for the user.
And I know what you're thinking. That sounds, well, obvious, right? Of course you shouldn't need a PhD in computer science just to ask a simple question about your own data. But you've got to remember, back in 1970, this was a mind-blowing, absolutely radical idea. So what was it about this simple concept of data independence that was so revolutionary? Why was this the key that unlocked, well, everything? That's what we're here to break down.
All right, here's the game plan. First, we're going to travel back in time to see just how tangled and messy the world of data was before Codd showed up. Then, we'll unpack his ridiculously elegant solution. After that, we'll see how it actually works, how it gave birth to a whole new way of talking to data, and finally, we'll look at the mind-boggling legacy this one paper left behind.
Okay, so first things first, let's really get our heads around the problem Codd was staring down. Before his relational model, the data itself and the programs that needed to use that data they were basically fused together. He had a perfect name for it: data dependencies. And it's perfect because programs were literally chained to the physical layout of the data on the machine.
So what did these chains actually look like? Well, there were three big ones. First up, you had ordering dependence. Imagine your program is built to expect a list of parts sorted by part number. Simple enough. But what happens if some admin decides it's more efficient to sort that file by price instead? Boom, your program just breaks. It's that fragile. Next, you had indexing dependence. Now, an index is just a trick to help the computer find stuff fast, kind of like the index in a book. But programs would get so used to a specific index being there that if you took it away, maybe to speed up something else, the program would grind to a halt or just crash. But the real monster, the biggest problem of all, was something called access path dependence.
See, back in the day, data was often stuck in these really rigid hierarchical tree structures. This example here, it's pulled right from Codd's paper. You've got your main file for parts at the top, and then, tucked away underneath each part, you've got a list of all the projects that use that specific part. So if you wanted to ask a simple question like, hey, which projects use this bolt, your program had to know the exact path, like a set of turn-by-turn directions, to navigate down that very specific branch of the tree.
And right there, that's the absolute heart of the problem. Your program's code, its actual logic, was completely intertwined with that physical data layout. You couldn't just say, get me info on project Y. No way. You had to hard-code the exact steps. Go to this file, then go down 3 levels, turn left. It was like giving directions through a maze. And what happens if the maze changes? Your software gets hopelessly lost. It was incredibly fragile.
So what if the database administrator has a better idea? What if they decide to reorganize things? Like this. Here, you've got separate files for parts, projects, and the commitments that link them together. Logically, it's the same information, just arranged differently. But that program we just talked about, the one with the hard-coded directions, it's toast, completely broken. It's searching for a path that has just vanished into thin air. That right there is access path dependence, and it turned any kind of database change or update into an absolute terrifying nightmare.
Okay, so you've got this complete mess, this tangled web of dependencies, and into this chaos walks Codd with a solution that is just shockingly simple. He said, hey, let's stop thinking about data based on how it's physically stored on a disk. Let's start thinking about it in terms of its logical relationships.
And the core building block of his entire idea was the relation. Now, if you read the paper, you'll see a lot of mathematical jargon about n-tuples and set theory. But honestly, for you and me, all you need to know is that a relation is just a table. Seriously, that's it. Think of a simple spreadsheet with rows and columns. That simple, beautiful idea is the foundation for everything that comes next.
And these tables, or relations, had a few very clear, very simple rules. Every row has to be unique, no duplicates. But here's the absolute game changer. The order of the rows doesn't matter at all. It's completely irrelevant. A row could be at the top, the bottom, or in the middle. Its information is exactly the same. With that one single rule, COD took a sledgehammer to that chain of ordering dependence. It's just gone.
So, if the order of the rows doesn't matter, how do you find anything? Well, that's where the primary key comes in. It's super simple. It's just one column in the table where every single entry is guaranteed to be unique. Think part number, or employee ID, or social security number. It's like a unique address for every single row. That key means you can always find the exact piece of data you need, no matter where it's physically sitting in the table.
Okay, so the big idea is to have all these simple, clean, independent tables. That's the dream. But what do you do with the messy, nested, tangled up data that everyone was already using? You can't just throw it away. Well, COD had an answer for that too. He laid out a step-by-step process, a recipe for turning chaos into order, and he called it normalization.
Just look at this thing. This is another example straight from his paper, and it is an absolute mess. You've got one single record for an employee, but buried inside it is a repeating list of their job history. And then, nested inside of that is another repeating list of their salary history for each job. And over on the side, you've got another list of their children. It's this kind of nested, tangled structure that was causing all the problems.
So how does normalization fix this? Honestly, it's like untangling a knotted necklace. It's methodical. You start with the main record, the employee. You find its primary key, in this case, the man number. Then you take that man number and you basically copy and paste it onto every single item in those messy nested lists. Once you've done that, you can just pull them out and make them their own separate flat tables.
And voila! Look at the result. What used to be one giant, complicated, tangled mess is now 4 beautifully simple, clean tables. You have one for the employee's basic info, one for job history, one for salary history, and one for children. See how each table is about one thing and one thing only? But, and this is the magic, they're all still connected. That man key acts like a thread linking them all together. All the data is still there, but now it's organized by what it means, not by some random physical layout. This right here, this is data independence.
Okay, so we've broken the chains. The data is now stored in these clean, logical tables. But that creates a new problem, right? How do you ask it questions? You can't give it those old step-by-step directions anymore because there's no fixed path to follow. You need a completely new way to communicate with your data. A language where you don't describe how to find something, but simply what it is you're looking for.
And COD had this brilliant analogy for it. He said that once the data is organized this way, the information is just there. It's like Everest. You should be able to attack it from any side. If you have a project name, you should be able to find all the parts it uses. If you have a part number, you should be able to find all the projects that need it. He called this powerful idea symmetric exploitation, and it was something the old tree-based systems were completely incapable of.
So how do you build a language like that? Well, COD proposed something he called a universal data sublanguage, and it was based on some pretty heavy-duty mathematical logic. But the core idea was simple. Stop telling the computer how to do its job. Instead, just tell it what you want. You should be able to just state your query as a logical condition. Something like, find all the rows where the state column is California and the part number column is 123. You just describe the answer you want, and you let the database itself figure out the smartest, most efficient way to go find it.
And that idea, that vision of a universal language that describes the what and not the how, that became the direct inspiration, the blueprint for what we now know as SQL, the structured query language. Yeah, that's right. If you have ever written a single line of SQL or used any tool that does, you are directly using a legacy that started with this paper in 1970. It's everywhere.
All right, so let's just pull back for a second and take in the big picture. I mean, the total impact here is, it's almost impossible to overstate. It is not hyperbole to say that this single, dense, academic paper from 1970 literally provided the blueprint for the modern digital world.
Think about what he did. COD's model shattered the link between an application and how its data was physically stored. That freedom, that independence, is what made it possible to create these incredibly powerful universal languages like SQL. And that 1-2 punch, the relational model plus a high-level query language, became the bedrock for pretty much every database system for the next 50 years. I'm talking everything from giant corporate mainframes all the way down to the apps on your phone. Without this fundamental breakthrough, the entire data-driven world we live in, every website, every app, every online service, it just wouldn't exist as we know it. It's that profound.
So, in the end, COD's great achievement was freeing our logical understanding of data from the physical chains of the machine. He gave data its first great freedom.
Which, really makes you think. As we stand here today, dealing with a whole new set of challenges, things like artificial intelligence, data privacy, giant corporate data silos, what's the next freedom that data needs? What's the next chain that needs to be broken?